Okay, so let's start. Um, so quick recap of what we saw in the previous class. We defined what a convex function is over R. So a function is convex if essentially you take any 2 points on the curve, the straight line joining those 2 points always lies above the curve itself. Right, so that's the geometric definition of convexity, and you can have a mathematical representation as defined over here. And we saw that if the function is twice differentiable, then there's a nice way of testing for convexity. Essentially, convexity is equivalent to saying that the second derivative of f of x at every point is always greater than or equal to 0. Right? So in other words, the slope of the curve keeps increasing. And we saw that suppose we wanted to do unconstrained minimization of a convex function, then that essentially corresponds to solving for the point where the first derivative or the slope is equal to 0. Right? So before we proceed to the higher dimensional case, let's see some simple algorithms which can be used to numerically minimize a convex function. All right. So each of these have geometric interpretations, and we'll see each of those. Again, it's not an exhaustive list of algorithms, but we'll see 3 different algorithms that are useful for solving convex optimization, but slightly more general optimization problems as well. So the class of problems that we'll see is going to take the following form. So the goal is always to find the minimum of f of x, where some f is some function over the reals. But now we'll assume that the minimum lies in some interval a0 comma b0. So this is what is given to us. That's what we will assume. So we've approximately located the minimum to within a certain interval, or this interval itself could correspond to some set of constraints. Okay, so the question is, suppose I want to solve this particular problem, then how do I go about solving this? So the first couple of algorithms that we'll see essentially try to reduce this search space. So right now the search space is the interval from a0 to b0, and we'll try to iteratively reduce this search space. So shrink this interval down in multiple steps so that we get down to a sufficiently small interval where this minimum is going to be located. All right. So again, we're given some kind of a function that may look like this. This is my x, this is my f of x, this is maybe my a0, and this is b0, and this is the point of minimum. My goal is to somehow find this, let me call this x star. My goal is to at least get this x star to within a certain error. It's okay if this, after all, it's a numerical algorithm, so I may not be able to get x star exactly, but I should be able to locate x star to within a certain epsilon, some error. Okay. So the first algorithm that we'll see is what is called the golden section search. Right. So let's try to see what the geometric intuition for this algorithm is. Okay. So let me take this particular function So I have my initial points A0 and B0. Let me construct two other points. So I'll take 2 points A1 and B1, where A1 is to the right of A0 and B1 is to the left of, B1 is to the left of B0. Okay. And suppose I evaluate the function at these 2 points. So basically at all these 4 points. Okay. So let's take this particular example. I'll try to contrast this with multiple examples. So this is what my function looks like. Okay. So in each of these cases, I want to basically shrink down my search space from A0, B0 to something smaller. Okay. So let me also have so I have A0, B0, which is my original search space. I take 2 other points arbitrarily, A1, B1, and my goal is to find out in which of these intervals the minimum could possibly lie in. Okay, or try to eliminate which of these intervals that the minimum could not lie in. Suppose that the minimum, the true minimum of this particular function, lies in the interval A0 to A1. Okay, maybe that would happen if I chose this over here. Okay. Again, remember that I can only evaluate the function at A0, A1, B1 and B0. So I have only 4 function values with me at this point. So if the minimum lies in this interval from A0 to A1, what can I say about f of A1, f of B1 and f of B0? Or in other words, what happens to the function to the right of the minimum? It's an increasing function, right? So if the minimum lies between A0 and A1, then f of A1 will be less than or equal to f of B1, and that will be less than or equal to f of B0. All right, that's for sure. Suppose that the minimum lies between B0 and B1. Then what can happen? What can you say about f of A1, f of B1 and f of B0? Yeah? The first 3 would be decreasing. But is it possible to have the minimum between B1 and B0 and still f of A1 is less than or equal to f of B1 is less than or equal to f of B0? Yeah? Okay, let's assume that it's not a constant function. So let's just write down our observations. So if the minimum x star is between a0 and a1, right, then f of a1 is less than or equal to f of b1 less than or equal to f of b0. Okay, but on the other hand, if x star lies in b1 to b0, f of a1 less than f of b1. Is this possible? Right, so what am I saying? Let's draw pictures because those are useful. So I have a0, a1, b1 and b0. Essentially what I'm saying is I evaluate these at the function at these 3 points. I have, say, f of a1, f of b1 and f of b0. Is it possible that the minimum lies between b1 and b0 if the function is convex? Why? Yeah?
A1 can be a point of
A1, that's okay. Strictly between A1 and B0. Sorry, can it lie strictly between B1 and B0?
Individually true, but not suddenly.
Which one?
Like A1 can be less than B0. The f of A1 can be less than f of B0.
Okay.
F of B1 can be less than f of B0.
Okay.
But all three counts.
No, I want it in this particular order. So f of A1 is the least, f of B1 is more than f of A1, and f of B0 is strictly more than f of B1. No, I'm going to assume that A0 is less than A1, which is less than B1, which is less than B0. I'm going to always choose it in this particular way. How many of you say that this is possible? That is, the minimum can be between B1 and B0. Firstly, is the question clear? So I have a convex function, okay, and I'm evaluating this at 4 points: A0, A1, B1 and B0, and they are ordered in this particular fashion. Let's just take these 3 points, f of A1, this is my f of A1, f of B1 and f of B0. When I evaluate the function at these 3 points, it turns out that f of A1 is less than f of B1 and f of b1 is strictly less than f of b0. So you can think of just these 3 points for pictorial. My question is, can the point of minimum, right, be between b1 and b0?
No.
Okay.
If we are not assuming continuity, then I have, let's say, something from the left of A1 up until A1.
Okay.
And then I can start at B1, let's say, and I'll have no values between A1 and B1.
So what do you mean no values
As
between?
in, it's discontinuous between. So as in let's say the range of the function.
The function is well defined at all these points.
Like if it's discontinuous, I can make some graph until A1.
Okay.
Have a discontinuity between A1 and B1.
Okay.
And then from B1, I can go down to whatever x star and then go up.
You mean something like this?
Even that, yeah. Not.
But is this convex?
That's why I was saying that between A1 and B1,
Correct.
I'll not have.
But you can't do that. So it's a function, right? So it's well defined in this entire interval between a0 to b0. For every x, there is some value. It's defined for all these points.
If it's just linear between A1 and B1,
Okay.
and then from there it's I'll have maximum.
So I'm saying it's convex, right?
But with the linearity, convexity is not lost.
Which,
It's piece, like if I define a piecewise function
yes,
between A1 and B1,
is every piecewise linear function convex? I mean, can you give me an easy example of a piecewise linear function which is not convex?
it is convex.
Minus mod x is not convex. So let's just take the line joining these 2 points, f of a1 and f of b1, and f of b1 and f of b0. Okay. You know that the function value, suppose that the function is actually convex, the function value should always be below each of these lines. Correct. So these 2 lines basically form an upper bound for the actual function itself. So now is it possible that the minimum lies in between b1 and b0? So the function value, the actual curve, lies below these lines. It's somewhere below, doesn't matter where it is. Okay, it could be it could be something like this or whatever. But can this point of minimum lie in this particular interval? Why?
If minimum exists in between B1 and B0, the right side function should be decreasing function.
The left side?
The left part would be decreasing function. Then f of A1 will not be less than f of B1.
Correct. So anywhere to the left of the minimum, the function should be decreasing. Correct. So if the minimum lies in between b1 and b0, it should be decreasing on the left. Correct. Which must mean that f of a1 should be greater than f of b1, which is not happening over here. Right? Is it okay? So if the function is increasing from a1 to b0, then it must mean that the minimum lies somewhere to the left of b1. It cannot be between b1 and b0. Right? So what I can do is I evaluate at these 4 points if the function is increasing from a1 to b1 to b0, then I can declare that the minimum certainly does not lie in between b1 and b0. Okay. Is it possible that the minimum lies in between a1 and b1? It is possible. Is it possible that the minimum lies in between a0 and a1? How many say yes? How many say no? Okay, why do you think that cannot happen? Correct. So if f of a1 is less than f of b1 is less than f of b0, is it possible that the minimum lies in between a0 and a1? So
Yes, yes.
it's possible, right? So you can have something, the curve looking something like this, in which case it will continuously be increasing. Okay, but the minimum could lie either in this interval between a0 and a1 or in the interval from a1 to b1. I can't rule out either case. Do you agree with that? So if f of a1 is less than f of b1, which is less than f of b0, then the minimum is going to lie in between a0 and b1. Okay, which means that now I can reduce the search space from a0 b0. I now come down to a0 b1. Now on the other hand, if f of a1 is f of a0 is greater than f of a1 is greater than f of b1, then what can you say about x star? So it will lie somewhere between, in which region? A1 to B0. Okay, so this much is clear. Now I can do this iteratively. Now I define, instead of looking at the interval a0 to b0, I can look at the interval from a0 to b1 or a1 to b0, and I can keep proceeding this way. Correct. So here is one algorithm. So you start with, you're always given an initial a0 and b0. Okay, and you're told that the function is convex. In fact, it turns out that convexity is not required. It's enough to have a function that is continuous and the derivative is equal to 0 only at one point, at the point of minimum. Which one? Not necessarily. It's enough to just have greater than or equal to. I'm sorry, can you?
Second inequality.
The second inequality. Okay. So suppose that this happens. So this is my A0, A1, B1, and B0. I find out that f of A0 is the largest, f of A1 is less than this, and f of B1 is less than this. Okay. Now, once again, I can the minimum can definitely not lie between A0 and A1. That's convincing. Again, by a symmetric argument. So the minimum must lie between A1 and B0. That's it. Right? Because the minimum should lie below these curves, right? And basically to the left of the minimum, the function is decreasing. So clearly, when you go from A0 to B1, the function is continuously decreasing. So that's you just eliminate this particular interval from your search space. Okay, so given these observations, we can come up with the following algorithm. So you start with an initial A0, B0, and then you take I equal to 1, 2, 3, up to some point of convergence until your search space has reduced sufficiently. And in each step, you do the following. If f of A0 is greater than or equal to f of A1 greater than or equal to f of B1, you set, sorry, I should do it the following way. So at this particular iteration, I have AI minus 1 and BI minus 1. So this is my search space in the ith iteration before I start the ith iteration. So in the first iteration, my search space is A0 to B0. Right. So now I have to shrink this particular interval. So I choose, let's say, AI prime to be equal to a I minus 1 minus some delta. Okay, sorry, AI plus delta. So basically I move to the right of AI minus 1 by delta. So initially I have A0. So from A0 I go to A1 by moving to the right by delta. And my BI prime is BI minus 1 minus delta. Okay. And now I just evaluate the function at these points, f of AI prime, f of BI prime, f of AI minus 1 and f of BI minus 1. Yes.
When you are evaluating AI prime, you start from A1 prime. A0 are initial values. So when you are taking AI minus 1, it should be A0.
Correct.
Right? For the first
Correct.
iteration.
Correct.
So A1 prime will become A0 plus delta. So it is basically moving from A1 to backwards. A0 plus delta will be before A1.
No, A0 plus delta will be to the right of A0, right?
But we are changing A1 prime as A0 plus something. A1 is shifting backwards.
So I haven't defined what A1 is yet. Okay. Again, just some notation. Okay. So basically I'm choosing this A1 and B1 here. So A1 is to the right of A0 and B1 is to the left of B0.
You can also make sure AI is less than BI.
Correct. So I have to choose this delta carefully enough. Okay, that I will do. I'll tell you how I choose this delta appropriately.
AI prime.
Yes, so I'll set it equal to AI after checking, basically. Okay. So if you'd like, I'll call these two AI prime and B1 prime. Okay. Let me Okay, so in each iteration, I run these steps. So if f of ai minus 1 is greater than or equal to f of ai prime, which is greater than or equal to f of bi prime, then I set ai equal to ai prime and bi equal to bi minus 1. Okay, so my original search space was ai minus 1 bi minus 1. Okay, my new search space is ai bi. Correct. So ai minus 1 bi minus 1 ai prime bi prime. So the function value is decreasing. Correct. So I can definitely rule out this particular interval, and this my new search space becomes this particular interval. Right. So I said ai equal to ai prime, bi equal to bi minus 1. Because I keep the right end as it is, I shrink the left end. Okay. And that's it. I keep repeating this until it converges. But now I have to be a little careful. I have to choose delta, as you rightly pointed out. So ai prime should be to the left of bi prime. That's something I have to ensure. Correct. So how do I choose? So the whole question is, how do you choose delta? Okay. In principle, I could just, so how to choose? So clearly I want ai minus 1 plus delta should be strictly less than bi minus 1 minus delta, which obviously means that delta should be less than, yeah, bi minus 1 minus ai minus 1 divided by 2. Correct. That's something I have to ensure. But is there a better way of choosing delta? Can I choose it arbitrarily, or can we do it in a more clever fashion? So if I choose too small a delta, what would happen? It takes a lot of time, right? It will take that because I don't shrink my interval too quickly enough. But what happens if I choose a really large delta? Potentially you could keep oscillating, correct? But also, if you think about it, we have to do a lot of evaluations, right? At every point, we have to evaluate f of x at these 3 points. Now, we don't have to evaluate at all 4 points because I already have f of ai minus 1 and f of bi minus 1 from the previous iteration. So in every step, potentially, I only have to evaluate f of ai prime and f of bi prime. Correct? So 2 evaluations per iteration. Can we reduce this to just 1 evaluation per iteration?
Use the midpoint then in a binary fashion.
Okay.
Use the midpoint, if one district is equal to the other.
Can you?
And then we have a set of AI minus 1 and AI minus 1 at the beginning of each iteration.
Okay, so let's start from the beginning. Let's start with A0, B0. Okay, so I have A0, I have B0. So how do you choose A1 and B1? Okay, fine. Let's take a step back, come back. Oh, sorry. You're right. It's not complete. So there's else. Yeah. Thanks for pointing that out. So otherwise, you set AI equal to AI minus 1 and BI equal to BI. That's correct. That was missing. Thanks. Okay, so any questions regarding the algorithm itself? Okay, so now let's come back to how do we choose delta. Now I have A0 and B0. Suppose I choose my A1 and B1. Okay, and it somehow turns out that the minimum lies in between A0 and B1. Okay, that's the first round. Okay, but now suppose I want, now I again shrink the interval from A0 to B1. Okay, to some other set of points, A2 and B2. Can I somehow choose this so that my A2 and B2 align in this particular fashion? Suppose I was able to do this at every stage. Okay, then what would it mean? It would mean that I know from the previous iteration the values of f of A1 and f of B1, and I also have f of A0 from the iteration before that. So all I have to do is just evaluate f of A2. That's the only one new evaluation that I have to do. So is it possible to always choose these AIs such that A2 equals, sorry, B2 equals A1? A1. That is, if it lies in the range A0 to B1. If it lies in the range A1 to B0, then I choose it so that A2 is equal to B1. Okay. Is it clear why I am trying to do this? Right? I want to minimize the number of it. If I am able to do this, say in this step, and I keep doing this, then in every stage I only have to evaluate this once. Correct? So this is just algebra. So let's assume that A0 equal to 0 and B0 equal to 1. Okay, so we have a unit interval and you want to shrink it down to A1 and B1. All right, and I choose A1 equal to A0 plus, let's say, rho, B1 equal to B0 minus rho, and A2 assume that we're operating in this particular case. A2 now lies in between A0 to B1. So this is A0 plus, let's say, rho into B1 minus A0, and B2 equals B1 minus rho into B1 minus A0. So essentially in every stage I'm shrinking the interval by a constant fraction rho. Now if I do this, and in other words, so this would be just B0 minus A0. If you want to take this B0 minus A0, now I want B2 to be equal to A1, or in other words, B1 minus rho times B1 minus A0 should be equal to A0 plus rho into B0 minus A0. Let us assume that A0 minus B0 is equal to 1, just so that our calculations become easier. So this is, I can again substitute for B1. This is B0 minus rho minus rho into B0 minus rho minus A0 equals A0 plus A0, which is just rho. Correct. So if I take A0 equal to 0 and B0 equal to 1, or just by rearranging, I get 1 minus rho into 1 minus rho equals rho. So the rho that satisfies this particular equation, what does this equation simplify to? What are the solutions of this? Sorry, rho square minus 3 rho plus 1 equals 0. So 3 plus or minus root 5 by 2. Which of these solutions should I choose? Hmm? 3 minus root 5 by 2. Correct. So it's between 0 and 1. In fact, it turns out to be, so I choose rho to be equal to 3 minus root 5 by 2, and that evaluates to 0.308 or something. Sorry, 382. Something. All right. So this means that I only need to evaluate at one point in every iteration. Correct?
Sir, how are we saying that we are reducing the evaluation to 1 instead of 2?
Okay. So clearly it's enough to evaluate at 2 points. Do you agree with that? Because you only need to evaluate at f of a1 and f of ai and f of bi. Correct? Now, suppose I use this particular approach. All right. I have a0, b0, and I have this a1 and b1. So initially, of course, I need to evaluate at all these 4 points. Suppose I do this. Okay. And the minimum lies somewhere in this particular interval from a0 to b1. Okay. Now I again further shrink this interval and I get a2 and b2. Okay. Now in the second iteration, how many points do I need to evaluate it at? I only need to evaluate at a2, correct? I don't need to evaluate at b2 because it's a1, which I had evaluated in the previous iteration. Correct? Okay, so suppose I now do this. All right. So my original search space, originally it was from a0 to b0. In the first, at the end of the first iteration, I reduced the search space to a0 to b1. I found 2 new points, a2 to b2, which turned out to be a1. All right. Now, suppose that it did not lie in this interval from a2 to a1. Okay. I again evaluated the 2 new points, and they happen to be, let's say my b2 is equal to a3, and some b3. Okay, and so on. This keeps happening. So when I go from the I minus 1th iteration to the ith iteration, either my ai is equal to bi minus 1 or my bi equal to ai minus 1. Okay, so in each iteration, I am taking ai, whatever my ai prime, to be equal to ai plus rho times bi minus 1 minus ai minus 1 and bi prime to be equal to bi plus bi minus 1 minus ai minus 1. My choice of row ensures that either this is equal to bi, this is equal to bi minus 1, or this is equal to ai minus 1. Okay. So if you're not convinced, let's just try that. Okay, so let's write some functions to just implement the golden section search from scratch. So what do I need? First, I need to evaluate the function, right? So let's say, let me define function value at x to just essentially return, let's take an example. So I'll say f equals x to the 4 minus 14 x cube plus 60 x square plus minus 70. Okay, so all this does is evaluates the function at any given point. Okay. Okay, so let's start with initial values. So suppose I want to minimize this function over the interval 0 to 2. So a previous equals 0, previous equal to 2. All right. Let's say I want to run this for 10 iterations. So I also want to choose row, which is going to be 3 minus root 2, sorry, 3 minus root 5 by 2. Okay. So in each iteration, what do I need to do? First, I need to compute my AI prime and BI prime. So what is AI prime? So a previous plus row into, correct. So B previous minus A previous. And my BI prime is B previous minus exactly this amount. Correct? Okay. Now let's say that I evaluated all of these 4 points. I don't need to, but I still do it. So let's see. So what is the first? How do I write the first condition? So I have to compute the function at, let's say, a previous and suppose that this is greater than or equal to the function value at a, right? And the function value at a is greater than the function value at b, then what should I do? So basically, in this case, where would the minimum lie? In which interval would this lie? So it's decreasing. So f of a previous, f of ai minus 1, f of ai, f of bi, it's continuously decreasing, correct? So the left end cannot have the minimum. So I need to set the left end to be equal to a. And the right end basically remains the same. I don't need to make any changes to the right end of the interval. If this doesn't happen, it will be b. Correct? So in every stage, let me print what this value is. Because this corresponds to which interval I am searching over. Let me just do this in the beginning of each iteration. Okay. Let me also print which cases.
The two cases.
Okay.
They can both.
Okay.
A0 greater than
Uh-huh.
A1 greater than B1.
Okay.
And then A1 less than B1 less than B0.
Okay. Can anything else happen? So suppose that this were not the case, right? It's not continuously decreasing on one side, right? So let's again take a picture. So if this doesn't happen, then it must mean that at some point, maybe it's increasing, right? This is one scenario, correct? But if this scenario happens, what can you say about f of xi minus 1? Can this be less than this particular value? If it is convex, it cannot, right? It has to be greater than this. So if this scenario happens, then it must be the case that it's increasing from B1, A1 to B1 to B0. All right. What is the other scenario that can happen here? Yeah. It's possible that it's continuously increasing, correct? This is possible. But then if this happens, then what can you say about f of b0? Can the function value at b0 be less than the value over here? Not possible, you will use convexity, so it has to be greater. So that's the only scenario. Can anything else happen? So I take some value over here. increase and then decrease. Can this happen? No, because the function is convex. Right? So the only scenarios are that either this keeps decreasing from a0 to a1 to b1, or it decreases and then increases, or it always increases. Correct? And in either of these two cases, either this case or this case, it has to be the case that these three values are always increasing. So it's enough to just check one condition, right? Okay, so maybe let me not print these for now. So initially I started with 0 to 2, and then I reduced that to 0 to 1.23. Right? In the next iteration, I shrunk it down to 0.472 to 1.23. So at how many points do I have to evaluate? Let me keep a track of that. In this particular case, right? It's enough for now. Yeah, fine. That's okay. A few extra points is fine. But I need to evaluate at 0, at 2. At this point, I've already evaluated at 0. So I only need to evaluate at this particular point. Here, I've already evaluated at this particular point. So I just need to evaluate at this point. Okay, maybe what I'm not keeping track of is what AI and BI are. Right, so or AI prime and BI prime are. Let me also print that. So initially I would need to evaluate at all of these 4 points. Let's see if we can make this more easier. Okay. So I need to evaluate at these 4 points. Okay. Now in this particular iteration, how many new points are added? One new point, or 2. There's only one, because 0.763 was already here, 1.23 was already here. So in the second iteration, I only need to evaluate at 0.472. Let's go to the next iteration. I've already evaluated at 0.472. I've also evaluated at 0.763. I need to evaluate at 0.944. I don't need to evaluate at this particular point. So I only need to evaluate at this point. Next iteration. this is the only point I need to evaluate at, because I've already evaluated at both these points in the previous iteration, and so on. This is happening. You'll see this trend happening in every iteration, right? So when I go here, this is a new point that is added. This point and this point are coming from the previous iteration. So in every iteration, I only have to evaluate at one new point, right? And by how much am I reducing or shrinking the interval? So I'm reducing it by rho into B0 minus B1. But in comparison to, so if I had to compare, let's look at Bi minus 1. So Bi minus Ai is the length of the current interval. What is it in proportion to Bi minus 1 minus Ai minus 1? So this was the search space in the previous iteration. And at the end of the current iteration, this is my new search space. So what is this equal to? How much will this be? This will always be 1 minus rho, because you have an interval of a certain length. You are cutting it by a fraction rho. You are throwing out that particular part, right? So if you look at this particular picture, so I have Ai minus 1, Bi minus 1. So if the overall length was equal to 1, then this is Ai minus 1 plus rho, and this is Bi minus 1 minus rho. And I'm either cutting out this particular fraction or this particular interval. In each case, this has length equal to rho. So what remains is 1 minus rho. So if I look at Bi minus Ai divided by B0 minus A0. So this was my search space before I started anything. And this is the search space after I iterations. What would this be equal to? This is 1 minus rho whole to the power I. So if I need to find the minimum to some desired accuracy, I can easily compute how many iterations are required, right? So to compute X star to some accuracy, let's say epsilon, how many iterations do I need? So at the end of whatever n iterations, my search space would be 1 minus rho whole to the power I, or 1 minus rho whole to the power n, and we want this to be less than or equal to epsilon. So what should be my n? Log epsilon to the base are you sure that's correct? Okay, fine. Both of them are negative. So log epsilon by log 1 minus rho. Correct? Or where I like it better is log 1 over epsilon by log 1 by 1 minus rho just so that both the numerator and the denominator are positive quantities. Okay, so in other words, then for a target accuracy of epsilon, you need to keep you need to run this algorithm for log 1 over epsilon iterations. Right? And we know exactly what the value of 1 minus rho is. Okay, so any questions? So this is one such algorithm wherein you keep reducing, you keep shrinking your search space by a fraction 1 minus rho, which is approximately 0.62. Right? Because we've chosen rho to be equal to 3 minus root 5 divided by 2. But in this entire algorithm, we only used to evaluate the value of the function. We did not need the derivative, we did not need the second derivative. Correct? So it's actually very powerful, because even if the function is not differentiable, we could still run this algorithm. So if the function is differentiable, then it turns out we can do something better. Right? And that gives us the so-called bisection method. So again, let's take a picture. Suppose I have this particular function and I start with my initial search space from A0 to B0. Now let us suppose I can now not just evaluate the function but also the derivative. Okay, if the midpoint, if the minimum lies in between A0 and B0, in between any interval, then what should be the derivatives at A0 and B0? Yeah, so the derivative at A0 should be negative and the derivative at B0 should be positive. Okay, now suppose I pick some other point in between. Let me call this C. Okay, and I find the derivative at C. If the minimum lies to the left of C, what should be the derivative at C? It should be positive. And if the minimum lies to the right of C, maybe if it's like this, then the derivative should be negative, right? So that gives us a natural algorithm, right? I have A0 and B0. I pick some point C in between and evaluate the derivative at this particular point. If the derivative is positive, then I know that the minimum lies between A0 and C. I can eliminate this particular region out. And I only need to focus from A0 to C. If the derivative were negative, then I know that the minimum lies to the right of C and I can eliminate this region out. Correct? I can keep repeating at every stage. So how do you choose C? What do you think is the best choice of C? The midpoint. Correct? So that gives us the following simple algorithm. which is you start with A0 and B0, and you always do the following. So on, take C equal to AI minus 1 AI minus 1 plus BI minus 1. Step. So I always take the midpoint, which is AI minus 1 plus BI minus 1 by 2. I take the midpoint. If the derivative of f at C is greater than or equal to 0, then what do?
Equal to zero, that would be the midpoint. That would be the midpoint.
Sure, if it were equal to 0, then I could potentially stop. So I could, if you want, I can add this condition. If it is greater than 0, then so BI equal to C and AI equals AI minus 1. If f prime of C is less than 0, then what is BI? BI minus 1 and AI equals C. Else you just stop and output C. Right, so let's try to implement the same thing. Okay, so what's the function? Let's take the same function as before, which is x to the 4 minus 14x cube plus 60x square minus 70x what is the derivative equal to? 4x cube. Can you see this? It's not clear. Minus 42x square plus 120x minus 70 Right? So I start with my a previous equal to um, 0, b previous equal to 2. Say I do it for 10 iterations. So what do I need to do? C. So C equal to A. Fine. Let me define by 2. If the derivative at C is greater than 0, this is equal to yes. What is A previous equal to? Do I need to change A previous? Yep. So B previous equals C. See? C, let's say is right. Let's say in every step I print the function value. Let's say C. Right. So I mean, after a certain point, there's not too much of a difference in the function value. But the main point is that from the previous scheme, from the golden section method, in this case, we're shrinking our search space by half. Right? Instead of shrinking by 0.6 something, we're shrinking it by half every single time. So this will converge much faster. So potentially, if you need a certain number of iterations for the golden section search, you will need much fewer iterations for this particular approach. But this comes at a cost. You should be able to evaluate the derivative at every single point. Okay. Any questions? Okay, so if not, let's stop here.